Today I'm going to talk about the basics of spectrum measurements. Although the techniques and settings I'll be discussing are common to almost any spectrum analysis hardware or software, I'll be demonstrating these concepts using SignalView PC. Spectrum analysis, or analyzing a signal in terms of amplitude versus frequency, has historically been the basis for many measurements made by RF engineers and is still widely used today. You can measure signal power, harmonics, occupied bandwidth, and channel power. And if you know what you're looking for, you can pick out input-related spurious signals, measure amplifier compression points, and characterize third-order intermodulation products. The four most fundamental settings for spectrum analysis are center frequency, reference level, span or acquisition bandwidth, and resolution bandwidth or RBW. The controls for these settings are along the bottom of the SignalView PC window. To change any of them, click on the field, type in the number you want, followed by the unit abbreviation, and then press Enter. Center frequency sets the location and frequency to which the analyzer is tuned. Span determines how much spectrum around the center frequency the analyzer can see. Reference level adjusts gain and attenuation settings in the signal path, allowing the analyzer to capture stronger signals without overdriving and see weaker signals with a better signal-to-noise ratio. Resolution bandwidth determines the smallest frequency separation that the analyzer can detect and has a strong effect on the noise floor of the spectrum display. I've got a signal at an unknown frequency between DC and 7.5 GHz. Let's find its center frequency and then look at it with a 2 MHz span and 1 kHz RBW. I'll go into the settings for the spectrum display and select the Max Span button. This lets me see the entire 7.5 GHz span in the RSA 507A that I'm using, although the max span will be different depending on the instrument you're using. I can then use a marker to find my signal. I'll right-click on the spectrum display and select Marker to Peak. Looks like my signal's at 1 GHz. Now I'll change my center frequency to match that. Reduce the span to 2 MHz, and change my RBW to 1 kHz. It just so happens that there are actually two signals here separated by a few kilohertz. Fortunately, my RBW is set low enough that I can detect both of these signals separately. I'm going to put a marker on each signal so I can see the frequency difference between them. 20 kilohertz. Now watch what happens when I increase the RBW to above 20 kHz. The two signals disappear and I'm left with a single odd-looking signal. Let's also take a look at the relationship between RBW and noise floor. Spectrum trace points are calculated by integrating the power over a given resolution bandwidth, so if you use a narrow RBW, you're integrating less noise for a given spectrum trace point, which results in a reduction of the noise floor. In general, decreasing the RBW by a factor of 10 lowers the noise floor by 10 dB. Although there comes a point where the noise floor of the measurement system itself prevents any further improvement via RBW reduction. Narrower RBW values result in longer capture times. The analyzer needs to capture at least as much time as the period of the RBW frequency to resolve that small of a frequency separation. The capture time is usually longer because the window factor needs to be taken into account as well. By default, Tektronix RSAs use a Kaiser filter shape for the RBW, which has a window factor of about 2.23. This means the analyzer has to acquire 2.23 microseconds of time to resolve a 1 MHz RBW. Because the acquisition bandwidth of the RSA 507A is 40 MHz, spans wider than that require the analyzer to sweep, or to change center frequency as it captures a wider frequency range in 40 MHz sections and stitches them together. This behavior changes based on the acquisition bandwidth of the analyzer being used. Be careful when setting the reference level. If it's too low, it can result in distortion of the signal or damage to the analyzer. And if it's too high, it can result in a poor signal-to-noise ratio. Best practice is to set the reference level a few dB higher than the integrated power in your span to maintain good resolution and to prevent damage. You can always use external attenuators to knock your signal down to a reasonable level if it's above the damage threshold of your spectrum analyzer's input. This video has provided direction on using the spectrum display for basic spectrum analysis. Thanks for watching.
Find out more at Vicom's website.